Greetings from Tufts University. My name is Jason Reif, and I'm faculty here in mechanical engineering.
My name is Liangchen Xu. I'm a fifth-year PhD student in the department.
We're here to tell you about our CPS grant, which is a CPS small project titled Software State Observability in CPS. And I do want to acknowledge another team member named Moses Huang, who is a recent PhD graduate from Tufts University in our computer science department. He did a huge amount of the work on this project, so credit where credit is due. Let's move on to the technical details of the project. The main focus of this project is safety critical software, for instance, aviation software. And these systems, it's very typical to do a significant amount of verification work up front before the software ever goes in service to make sure it's safe. Right? This takes up a huge amount of the cost of producing the software, just doing that verification. We'd like to see that software be able to move into service much sooner, quicker, and more cheaply without requiring nearly the intensity of verification and still maintain safety. And our approach to do this, our idea here, is to be able to understand enough about how information flows through a code that we can build a software bug detector that would run online while the software is in service to detect the few rare bugs that manage to pass through an initial screening for bugs. So there'll still be some verification up front, but much less so than there would normally be, right? With the idea that the bug detector will find out if there's an anomaly and switch the system into a reversionary mode using a very compact, perhaps formally verified kernel of code to make sure it can stop operations safely. Perhaps if it's a unmanned drone, to land safely at the nearest available landing site, right? Which would remove the threat without requiring us to verify all of the sophisticated flight management system code in advance. Right? So that's the idea of operation. In order to do our testing, we're going to look at a very specific piece of flight code called Autopilot, which is an open source flight management system that's available to all online and which has a very good bug database that we can use to inform our subsequent work.
In this research, we construct a bug detector using the machine learning model. So this bug detector depends on selecting right amount of variables to monitor. So in order to balance all the requirements we need, here includes overhead, computational overhead, sensitivity, specificity, coverage, and also alert time. So this becomes an optimization problem. By selecting because the selecting variables is not trivial, because if you select all the variables, so you have the large impossible computational overhead. If you select less, so you cannot cover all the requirements. So here we have a simplified version of this problem, using the program slicing technology to select the appropriate set of variables to monitor.
So in order to test this concept, we trained on the Autopilot code using both real bugs and injected bugs. In the specific experiments that we show in our poster associated with this year's update, we show some work related to a specific bug that it's listed in the Autopilot bug database as bug 7062. This involves a transition in flight modes from one mode to another during a vertical climb on a kind of a specialized type of aircraft that can do a vertical climb and transition into straight and level flight from there. So we took that bug and a number of other injected bugs that were in conditional statements. So we put these bugs into a conditional statement so they wouldn't execute quite the way that they were supposed to. And then we ran the bug detector, having been trained on nominal runs, to see if it could catch an occasional injected bug.
So from the result here, so we can say using the program slicing, we can significantly reduce the computational overhead by 90%, but also keep almost the same performance using all the variables to monitor.
So this is hitting a number of our goals. It was a reduced experiment that we ran here in terms of not trying to test everything. We didn't test coverage. We didn't test alert time. But we focused on sensitivity and specificity and met some baseline goals with a very simple machine learning algorithm. and also kept our overhead as low as possible, involving as few as 30 variables in some cases. So, what's important here is we used a very simple approach in this initial foray. In the future, our intent is to be able to adapt this method to include more sophisticated machine learning methods, more information over time. This was information from a single snapshot of data, one epoch in time, in order to increase our performance. So there's a lot of room there for increased performance moving forward. But I think the key message here is that we have a proof of concept where we were able to show that this kind of bug detection is possible using real software and real bugs.
Yeah, that's exciting. So we'll look at where we go next, I guess.
So stay tuned for next year's update, and you'll hear more about the progress on this project.